look up at the night sky and we see all these stars scattered around, and most people seem to think it's completely natural that maybe aliens are out there visiting us, or that eventually we'll be visiting them. But when you actually sit down and think about the physics, really think about it, you realize something quite remarkable. The universe has built in some barriers that make this whole idea extraordinarily difficult. And I want to tell you about 3 of them. Now, people sometimes think that the reason aliens can't visit us is just because of technology. Like, oh, maybe in 100 years we'll figure it out. Or they must have some super technology we don't understand yet. But that's not quite right. The barriers I'm going to talk about aren't technological barriers. They're physical law barriers. They're fundamental, and that's what makes them so interesting. The first one, and it's probably the most famous, is the speed of light. Now, you've probably heard that nothing can go faster than the speed of light. Light travels at about 300,000 kilometers per second. That's incredibly fast. In the time it takes you to blink, light could circle the Earth 7 times. But here's the thing. The nearest star to us, besides our own sun, is about 4.25 light years away. You know what that means? It means that if a spacecraft left Earth traveling at the speed of light, which is impossible, but let's imagine it, it would take 4.25 years just to get there. And that's just the nearest star. The distances between stars are so unimaginably vast that most people can't really picture them in their heads. Let me try to give you a sense of scale. Imagine the Earth is a marble sitting on a table. Now imagine the sun is another marble, and you put it about 20 meters away. At that scale, the nearest star would be somewhere around 1,300 kilometers away. You see how far apart things are. And there are billions and billions of stars in just our galaxy. But the speed of light barrier isn't just about distance. There's something deeper going on. You see, Einstein figured this out about 100 years ago, and it's one of the most profound discoveries in physics. As you push an object faster and faster, approaching the speed of light, something peculiar happens. The energy you need to accelerate it increases not just a little bit, it increases enormously. It's not like pushing a car on the highway where, to go twice as fast, you need maybe twice the energy. No. As you approach the speed of light, the energy requirement grows without bound. Let me explain how this works. Imagine you have a spacecraft of some reasonable mass, maybe 10,000 kilograms. You want to accelerate it to 90% the speed of light, just 90%. You can calculate how much energy you'd need, and it turns out to be absolutely staggering. And if you wanted to go even faster, say 95% the speed of light, the energy shoots up dramatically. And if you keep trying to push it faster and faster, approaching the speed of light itself, the energy requirement approaches infinity. It's not a little bit more energy. It's infinite energy. This isn't a limitation of our current technology. This isn't something we can overcome with a better battery or a more efficient engine. This is built into the fabric of space and time. When Einstein worked out the mathematics of special relativity, he discovered that energy and mass are related. You've probably heard the equation E equals mc squared. That means energy equals mass times the speed of light squared. The speed of light is about 300,000 kilometers per second. When you square that, you get an enormous number. So even a tiny amount of mass contains a huge amount of energy. The way this works in terms of acceleration is this. As an object moves faster, its relationship with the rest of the universe changes. It's not that the object itself gets heavier. Exactly. That's a simplification physicists used to use, but it's not quite right. What happens is that as an object approaches the speed of light, more and more of any force you apply goes into increasing its momentum rather than increasing its speed. The resistance to acceleration gets stronger and stronger. Eventually, when you're approaching the speed of light, you'd need infinite force to accelerate it any further. Now think about what this means for an alien civilization trying to visit us. They'd need to build a spacecraft, load it with people or cargo, accelerate it to some significant fraction of the speed of light. Maybe they could do 90% of light speed with some super advanced technology. But even at 90% the speed of light, the amount of energy required is absurdly large. We're talking about energies that exceed the total energy output of human civilization for entire years, just to accelerate the spacecraft. And that's one way. To decelerate at your destination, you'd need the same amount again. To make a round trip, you'd need it again coming back. And this scales catastrophically. If you want to go faster, say 99% the speed of light, the energy requirement gets many times larger. The 99th percentile versus the 90th percentile is a massive jump. Keep in mind, no matter how much energy you put in, you can never actually reach the speed of light. You can only approach it. The speed of light is an absolute barrier, not because something is in the way, but because of the fundamental structure of space and time. So that's the first law we're up against. The speed of light. Not that you can't go fast. You can go pretty fast if you have enough energy. But every fraction of percent faster you want to go costs exponentially more energy. Now, the second barrier is related to the first, but it's slightly different. It's about energy. Not just the energy to accelerate, but the total energy available in the universe and what it takes to maintain a spacecraft traveling at these speeds. This is where it gets really sobering. Let me ask you something. How much energy would you need to send a spacecraft the size of a car, about 1,000 kilograms, to our nearest star at a reasonable speed, carrying people? There are some proposals out there. Actually, some scientists have thought about this. One idea is to use lasers to push a tiny spacecraft, really tiny, maybe just a few grams, to around 10% the speed of light. It would take decades to reach the nearest star, but it's theoretically possible with current physics. But here's the problem. When physicists actually calculated how much energy this would take, they found something shocking. The energy required would be absolutely enormous. We're talking about quantities of energy that make our current entire global energy production look insignificant. The physicist Freeman Dyson, brilliant guy, he said something that I really like. Chemical fuels are hopeless for interstellar travel. He meant that burning fossil fuels, nuclear fission, nuclear fusion, all of these are microscopic compared to what you'd actually need. Think about it this way. Every substance in the universe has energy. Even sitting still, even at rest, every object contains mass energy according to E equals mc squared. A kilogram of matter contains about 21 kilotons of explosive energy equivalent just sitting there. That's 20 kilotons of TNT. A single kilogram. You could convert a paperclip into the energy of the Hiroshima bomb. But the thing is, we don't have a practical way to do that. And even if we could convert all the mass of a spacecraft into pure energy, we'd still have enormous constraints on how fast we could go and how much energy we'd actually have available. But there's something else. Even if a civilization somehow had access to unlimited energy, imagine they could just harvest energy from stars or black holes or some other incredibly advanced method. They'd still face this problem. In deep space, far from Earth, far from our sun, any spacecraft is on its own. It can't get resupply. It can't get new fuel. Whatever you're carrying with you is what you have to work with. And space is a very hostile environment. Dust particles become weapons at high velocity. Cosmic rays, high-energy particles from supernovae and other cosmic events. They bombard your spacecraft constantly, degrading materials, damaging electronics, being dangerous to any biological organism. These are not new problems that future technology will solve. These are features of the physical universe. There's also entropy. You've probably heard of entropy. It's the tendency of things to become more disordered over time. In practical terms, this means energy always gets wasted. Every system, no matter how efficient, loses energy to heat. A spacecraft is a machine, and machines degrade. The longer the journey, the more degradation. For a journey to the nearest star at even 10% the speed of light, we're talking about several decades. Micrometeorites, radiation, thermal stress, all of these things wear on materials. You'd need redundant systems, backup systems, repair mechanisms. All of that adds mass, which requires more energy to move. You get into this vicious cycle. Now, imagine if an alien civilization wanted to send a generation ship, a spacecraft that would travel for centuries or thousands of years. The creatures that arrive wouldn't be the same creatures that left. Life on a closed space system, in microgravity, under radiation exposure. You're not looking at human conditions anymore. And machines don't last forever. We have spacecraft that we've built, Voyager 1, for example, that are still functioning after more than 40 years, which is remarkable. But eventually, everything breaks down. Electronics corrode. Materials fatigue. It's not a question of technology, it's a question of physics. Time itself wears on things. So the second barrier is really about availability of energy and the degradation of systems over the distances and times required. You need so much energy just to get somewhere, and then your systems are wearing down the whole time you're traveling. Now here's where it gets truly interesting. The third barrier, and this is the one that I think people understand the least, is the scale of the universe itself combined with the limitations of biology and time. This is the one that really stops everything. Let me start with this. The universe is not just big. It's so big that your brain, which evolved to understand the savannas of Africa, literally cannot picture it. You can know intellectually that it's huge, but you can't feel it. Let me try to help you feel it anyway. The nearest star, Proxima Centauri, is 4.37 light years away. That means that light, the fastest thing in the universe, takes 4.37 years to reach it. If you traveled there at half the speed of light, which would require energy in the realm of impossibility, it would take you about 9 years. That's assuming you don't slow down for any reason. But if you arrive at Proxima Centauri at half the speed of light, you're moving unbelievably fast. You'd overshoot. You'd need to decelerate, which uses more energy, more time. The next nearest stars are even farther away. In our galaxy is about 100,000 light years across. That's not the universe. That's just our galaxy. There are billions of galaxies in the observable universe, each containing billions of stars. When you look up at the night sky on a clear night and you see a few thousand stars, you're only seeing a tiny fraction of what's out there, and you're not seeing the distances at all. You can't see distance by looking up. It's a two-dimensional view of a three-dimensional universe. So here's the problem. Even if you could overcome problems 1 and 2, even if you had a spacecraft that could travel at, say, 50% the speed of light, which you can't, but let's imagine, and you had unlimited energy, which you don't, you'd still face the fact that the nearest interesting star systems are decades away. The next ones are centuries away. The vast majority of the galaxy is thousands of years away. And in 1,000 years, things change. Human civilizations rise and fall. Species evolve. Technology becomes obsolete. Now, relativity adds another wrinkle to this. Einstein discovered that time is not absolute. Time passes differently, depending on how fast you're moving. If you travel at 95% the speed of light, time passes more slowly for you compared to someone at rest. This sounds like it might help. Oh, great. Time will pass more slowly. The trip will be faster. But it doesn't actually work that way. From your perspective in the spacecraft, the trip takes just as long as always. But from the perspective of people on Earth, you're aging much more slowly. By the time you arrive at a distant star, Earth might have aged thousands of years while you've aged only a few hundred. Everyone you knew is dead. Civilization might be completely different. But here's the cruel part. This only helps if you're traveling at very high speeds, very close to the speed of light. And we've already established that this requires absurd amounts of energy. Also, you can't go faster than light, so you're still limited. And the distances are still huge. Now, here's where biology comes in, and this is important. Life, as we understand it, is fragile. It evolved on Earth under very specific conditions. We need gravity. We need protection from radiation. We need air to breathe. We need water. The human body, specifically, is adapted to Earth conditions. Spend a few months in zero gravity, in orbit around Earth, and your muscles atrophy, your bones lose density, your cardiovascular system changes. An astronaut returning from the International Space Station, which is only a few hundred kilometers away, can barely walk when they get back to Earth. Now imagine traveling through space for years. Your body would be damaged in ways we can barely understand right now. And cryogenic freezing. Freezing people so they can survive the journey. That doesn't work. You can't just freeze a human being and thaw them out. The ice crystals that form rupture cells. The systems in your body that require water and dissolved materials. They're destroyed by the freezing process. We can freeze small tissues for short periods, but we can't freeze a whole human and revive them. That's not a technological problem in the near future. That's potentially impossible without changes to what humans are. Could an alien civilization have solved this? Maybe. Maybe they've become robots or uploaded their minds into computers. But then you're talking about artificial beings that might not have emotions, might not have consciousness in the way we understand it. You're talking about machines, really. And machines break. They need maintenance. They degrade. Some scientists have thought about generation ships, Enormous spacecraft that would travel for centuries, with multiple generations being born and dying aboard. But this introduces new problems. You'd need social stability for centuries or thousands of years. You'd need genetic diversity to prevent inbreeding. You'd need culture to be preserved. You'd need to maintain equipment and systems designed by your distant ancestors, equipment whose purposes you might not even fully understand anymore. You'd need to make sure that after 10,000 years in space, with no contact with home, your descendants still want to go to their destination and haven't decided to turn around and go back, or just settle on some random asteroid somewhere. Biologically, genetically, psychologically, the human species isn't equipped for this. And I suspect any biological organism would face similar limitations. This is where something interesting comes up. Some people imagine that if a civilization could just harness enough energy, like the energy of a sun or energy from a black hole, then they could do anything. They could overcome all these problems. But I don't think that's right. Energy isn't magic. Energy doesn't let you break the laws of physics. It just lets you do more work within those laws. Let me give you an example. You could imagine a civilization that takes apart an entire star and uses all of its energy output to power a spacecraft. That's an incomprehensibly large amount of energy. But even with all that, you can't accelerate a spacecraft to the speed of light. You approach it asymptotically, like a curve that gets closer and closer but never touches. At some point, you've put in so much energy that the returns are minuscule. You'd be accelerating for centuries at great cost just to shave a few more decimal points off the speed of light. And even if you could get a spacecraft to 99.9% the speed of light, the distances are still so vast that many journeys would take decades or centuries. Any civilization trying to maintain contact with multiple star systems would have the speed of light against them for communications too. Messages would take years to arrive. There's an old concept in science fiction called the Fermi paradox. The physicist Enrico Fermi asked a simple question: where is everybody? If the universe is so vast, if there's so much time for civilizations to develop, why haven't we detected any sign of alien civilizations? Why haven't they visited us? Why is there this silence? The usual answer people give is something like, well, maybe we're the first intelligent species, or maybe they're too far away, or maybe they're hiding. But when you look at the physics, a much simpler answer emerges. Maybe intelligent species simply can't visit each other. Maybe they can't even communicate easily. Maybe the universe is arranged in such a way that it practically guarantees isolation. Think about it. You'd need a civilization that invents radio astronomy or radio communication around the same time as us. You'd need them close enough, within a few hundred light years at most, so that radio signals could reach them in human timescales. You'd need them to be at the same technological level as us, more or less, because the advantages of being millions of years more advanced might mean they expand and develop in directions we can't predict. And you'd need to both decide to try to communicate at the same moment in cosmic time, both willing to spend the enormous resources it takes to send signals across light years. The probability of all of that is vanishingly small. And that's just for communication. For actual physical travel, the problems multiply. Now, let me be clear about something. I've been talking about three barriers: the speed of light, energy availability, and cosmic scale. But they're really all manifestations of the same underlying reality. They're all consequences of the fact that space and time are woven together, that the universe has a fundamental speed limit, and that the universe is vast beyond human comprehension. These aren't separate problems. They're aspects of the same problem. And here's the beautiful thing about this. This isn't speculation. We're not guessing. This is established physics. This has been tested over and over again. We've built particle accelerators that accelerate particles to nearly the speed of light, and they behave exactly as Einstein predicted. Exactly. The energy requirements increase just as the theory says they do. We've confirmed these principles in 1,000 ways. They're as solid as science gets. Now, none of this means that interstellar travel is absolutely impossible. The laws of physics don't forbid it, but they make it so difficult, so expensive, so time-consuming that you have to ask, why would any civilization bother? What would be worth it? There might be minerals on a distant star. There might be scientific knowledge worth gaining. But you're investing enormous resources, generations of effort, all to maybe get something that's valuable to you. while fighting against physics the entire time. For most civilizations, most of the time, the rational choice would be to stay home. I find this oddly comforting, actually. It means that the Earth and humanity and the life here has some special isolation. We're not constantly threatened by invasions from other star systems. The universe is big enough that we have space to develop and grow without constant interference. And if we ever do make contact with another intelligent species, which would be remarkable, it will probably be through radio signals or some other form of communication, not through physical visits. The conversation will be slow, limited by the speed of light, but that slow conversation might be one of the most profound experiences our species ever has. The physics of the universe has built in a kind of privacy. Each civilization, each solar system, is isolated by the vast distances and the fundamental laws. We have to work with that. We have to understand it. And once we do understand it, it changes the way we think about our place in the cosmos. We're not a vulnerable species waiting to be conquered by superior aliens. We're a species developing on a world isolated by physics itself, with the opportunity to figure things out at our own pace. That's not a curse. That's an opportunity. The next time you look up at the night sky and see all those stars, you might think about this differently. You might think about the vast distances. You might think about the speed of light, traveling at 300,000 kilometers per second, taking years just to reach the nearest star. You might think about the impossible amounts of energy required to go that fast. You might think about the time dilation, the radiation, the hostility of space, the fragility of life. You might think about how profoundly isolated we are. But you might also think about how remarkable it is that we can even figure this out. That we can sit here on this planet and understand these things about the universe through mathematics and experiments. That's the real magic. Not faster-than-light drives or alien invaders. The magic is that we can understand. We can think about these things. We can reason our way through the universe's constraints and come to understand them. That's what makes us human. That's what makes science worth doing.